Jeanette, are you on mute?
I was on mute, yeah. Okay, so I think I'm just looking at the green, but the red, so when I just start, right?
So we're live now. Go ahead.
Oh, okay. Okay. Good afternoon, good morning, everybody, wherever you are. Thank you for joining our webcast, the Water Research Foundation webcast project 4962, managing intracellular cyanotoxin release during oxidation processes in drinking water treatment plants. I think that is a project that is about to be finished. The publication is going to be coming very soon. We have really a great ensemble of authorities in the field of cyanotoxins, and I think it's going to be really exciting to listen to them and learn. I'm not going to spend too much time talking about technical because I think we'll have our great speaker, but I have some housekeeping items. The first one is that you can submit your questions throughout the webcast in the Q&A session, during and at the end of the webcast. So one thing I want to remind you, not yet, but there will be a survey at the end of the webcast, and we really encourage you to fill the subscribe. That's going to help us really improve and meet your needs. So I think it's very important. Just a reminder that the recording and the audio, the recording of the webcast, audio and visual, will be available if you go to the Water Research Foundation website, www.waterrf.org. And if you have questions about PDH, please contact Michelle Suazo at Water Research Foundation, and you see her email here, and she will give you the information how to get PDH. Okay, so this is just a visual sharing. I think you have seen already. If you want to ask questions at the lower right of the screen, you can enter your question here, and we'll be answering them at the end of the webcast. As to download the webcast, you can go and then download the presentations at your wish. Okay. So before I go and talk about this specific project, I would like to remind you that the foundation has done, I was speaking too much, a lot of work on cyanotoxins. We have done that since the 80s, and there are a lot of projects that we have done, especially with the Australian, and this is just an example of pictures of the report that are available on our website. There is the International Guidance Manual, and there is also a very practical thing, what is a utility manager guide for cyanotoxins. Those will be available on our website. So those are the projects that are completed. Now we have more recent project, and they have been informing our research planning. One is about communication, or the other one is about cyanotoxin expert workshop. And then and we have a project that is focused on the first one on your left, performance evaluation of cyanotoxin, and that's going to be a very good project as it evaluates the bioassay, especially the ELISA, the strength and weaknesses, very informative. The projects that are completed, we have assembled them in what we call a state of the science, and this is just a picture. So if you go to our website, you'll find a summary of every project since we started doing work on cyanotoxin, every project that is finished, that you can get information, and you can get the report from our website once we have that. What we have done in the last 3 years, the foundation, especially after the Toledo event and after the health advisories from the EPA, we have created what we call a focus area. Now we call it a research area that deals with cyanotoxin. That means it's a research program that deals only identified projects for the next few years on cyanotoxin. This focus area is called Cyanobacterium blooms and cyanotoxin, monitoring, control, and communication strategies. The general goal of the focus area is to develop a toolbox to help utilities to handle cyanobacterial blooms and cyanotoxin, and we are after practical, cost-effective control strategies and risk communication strategies. The focus area will include cyanotoxin from source to tap. This is, we always need multi-barrier strategies to handle cyanotoxin. It goes from source water protection through early warning, monitoring, treatment, implant, and in reservoir treatment, and finally, what is very important, and how to inform the public. So it's a multi-barrier thing. So I'm not going to spend too much time. This is 3 projects that some of them, this one, it's refinement and standardization of cyanotoxin method. It has been ongoing. It's not finished, and it's going to be evaluating not only chemical, instrumental, but also biological methods, standardize the methods, and develop guidance for utilities. The second one that is just starting, and Dr. Eric Wirth will give you, will tell you a little bit about it. It is guidance for evaluation and implementation for control HAB in surface water. So barely started. The next one that is also very important, and we may actually ask utilities to help us participate in this project, is lessons learned, is utility response to cyanobacteria, cyanotoxin event, case studies, and lessons learned. We want to learn from the case studies that worked well and the case studies that didn't work, because we always learn from the things we haven't been successful at. So I'm not going to go now. Without further ado, I'm going to talk to the things you've been waiting for, which is the technical component of the project. And as I said, we have a great ensemble of speakers here, but I am going to introduce just Dr. Eric Wirth, and then he will introduce his team for that. So Dr. Eric Wirth, a lot of you know him already. He's a project manager at the Water Quality Research and Development Group for the Southern Nevada Water Authority. He also serves as he's the current president of the International Ozone Association, Pan American Group. He's very busy. Dr. Wirth, I like to call him Eric. He received his Bachelor in Civil Engineering from West Virginia University, a Master in Environmental Engineering from Penn State, and a PhD in Civil Engineering from the University of Colorado at Boulder. He's a licensed professional engineer in the state of Nevada. He has worked exclusively with advanced treatment processes. It's a long bio, but so I'm going to skip a few things. The bios, and I'm not going to go through that. The bios are available for you. So if you want to know more about our speakers, you can go and then check for them. So I'm just going to say the last thing I want to say, and it's not enough. Dr. Wirth, he served as a principal investigator and co-principal investigator on several Water Research Foundation projects, and this is only one of them. Okay, Eric, it's your turn now. Thank you, and you can speak.
All right, thank you for the introduction, Jeanette. So today we will be discussing the outcomes of Water Research Foundation Project 4692, which investigated intracellular cyanotoxin release during oxidation processes in drinking water treatment plants. So in the next few slides, I'll give an overview of the topic. We'll cover some definitions and present the overall objectives for the study that you'll be hearing more about during the webinar. But first, as Jeanette said, I'd like to introduce our project team, starting with Dr. Katie Greenstein. Katie was a postdoctoral researcher at the Southern Nevada Water Authority here at the time of the study, and now she is a chemist at Des Moines Water Works. And Katie will be discussing cell lysis methods as well as the effective stagnation time on the webcast today. Next is Dr. Arash Zamyati, who is an assistant professor at Polytechnic Montreal. And Arash will be discussing oxidation of naturally occurring cyanobacteria cells. Next on the list, Dr. Eric Rosenfeld, who is Director of Drinking Water Process Technology at Hazen and Sawyer. And Eric will be discussing the Utility Guidance Manual on the webcast today, and that is one of the primary products of this project. And finally, Dr. Craig Adams, who's a professor in the Department of Civil Engineering at St. Louis University. And Craig will be discussing the AWWA CyanoTOX model. I'd also like to acknowledge our Project Advisory Committee members, Saeed Chowdhury, Barry Rosen, Sarah Page, and Carol Walchik for their feedback along the way. So let's get started with a few definitions that will be important throughout the remainder of the webinar, starting with what are intracellular and extracellular cyanotoxins. And let's focus first on the extracellular toxins. These are found outside of the cell wall in the surrounding water. And the treatment of many extracellular cyanotoxins has been studied for decades. And the table that I'm showing in this slide shows general oxidant efficacy for 3 common cyanotoxins: microcystin, cylindrospermopsin, and anatoxin A. An expanded version of this table, along with some other cyanotoxins, will be included in the guidance document, the final deliverable for this project. The other side of that are intracellular cyanotoxins, and these are found within the cell wall and have not yet been released or excreted into the water supply. And these are important. With the 10-day drinking water health advisories established near conventional method reporting limits, the release of this intracellular cyanotoxin could be very relevant for water treatment plants, to the point that even small releases of intracellular toxin could exceed the health advisory. So another way of thinking about intracellular toxins may be thinking of these as kind of like a Trojan horse entering your water treatment plant. There are many guidance manuals that exist from different agencies, including AWWA, US EPA, Health Canada, World Health Organization, etc. And they all touch on the treatment or management of intracellular cyanotoxins, and they're all pretty consistent with their guidance in that they all recommend avoiding or minimizing the use of oxidants to prevent release of intracellular toxins. However, that may not always be an option for utilities. There are many applications of preoxidation in water treatment plants. For example, disinfection, control of invasive species, biofilm control, inorganic and organic contaminants. So in some cases, turning off a preoxidant may not always be an option. In fact, there may be a tendency to increase dose in order to potentially utilize one of the best treatment techniques or barriers you have available to you in your plant in order to protect public health. So depending on that oxidant efficacy table that I showed earlier, an oxidant may be one of the best barriers for treating extracellular toxins. So this dynamic really created the need to research and better understand the treatment or oxidation conditions resulting in the release of intracellular toxins. And this led to our first project, Water Research Foundation Project 4406. So this was performed between 2011 to 2013, and we collaborated with the University of Colorado and Fluid Imaging Technologies. We looked at 3 laboratory cultured strains of cyanobacteria. As you see them listed there, Microcystis, Oscillatoria, and Lingbia. These strains each produce different metabolites. So for example, microcystin, MIB, and geosmin. So we also included taste and odor compounds. And each of those different strains of cyanobacteria had different morphologies or cell structures associated with them, which proved to be an interesting dynamic of this study. Next, we looked at 4 different oxidants: ozone, chlorine, chlorine dioxide, and chloramine. And we measured cell damage. We measured the release of those metabolites that I mentioned, as well as the release of dissolved organic carbon. Another aspect of this study, we actually extracted that intracellular organic carbon and performed some disinfection byproduct testing, some formation potential tests using that material. So all of that is contained in that final report, which has been published, and it's available through the Water Research Foundation. And it answered a lot of questions, but it also identified some additional research gaps, which led to the project that you'll hear more about today. And that is Water Research Foundation Project 4692. And during this project, we focused more on naturally occurring cyanobacteria samples. And that proved to be quite challenging, first finding out about the blooms and then mobilizing quickly enough to go out and grab samples to work with in the lab. Next, we evaluated immediate and delayed release at lower oxidant exposures. And this follows some work performed by Craig Adams regarding stagnation time, which is a very important variable when partial cell damage is achieved. We included some additional treatment chemicals, for example, permanganate, as well as reservoir treatment chemicals, hydrogen peroxide, and copper sulfate. And lastly, we were able to produce some preliminary guidance regarding the treatment conditions needed to promote release and subsequent oxidation. We call this a release and treat approach, which you'll hear more about on the webcast. And that occurs when we intentionally release the intracellular toxin and subsequently oxidize or treat it through a downstream process. And both steps are important for that type of approach to work. So with that, I will now turn it over to Dr. Katie Greenstein to discuss some of the methodology that we used for the project.
Thanks, Eric. So I'll be talking first about cell lysis methods that we assessed, and this is for extracting total cyanotoxin from cells, looking at intracellular and extracellular toxin combined. So to do this, we cultured a UTEC strain of Microcystis aeruginosa. It was a confirmed microcystin LR producer. And from there, we looked at low, medium, and high cell densities to look at how cell density impacted extraction of cyanotoxins for measurement of total toxin. We also looked at 20 parts per billion microcystin LR as a control, so we wanted to make sure the processes we were looking at did not degrade microcystin. And we also spiked the highest cell density into Colorado River water, so it had some background VOC and turbidity, and wanted to make sure that our cell lysis methods still worked properly. So the methods we looked at were freeze-thaw, microwave sonication, and chemical lysis. We selected these 4 methods after a careful comb through the literature and found that these were commonly used. And so to assess these, we were looking at 10 ml samples of the Cyanobacteria suspensions placed in 40 ml amber glass vials. So when we looked at freeze-thaw, we were using a standard laboratory freezer that was at negative 20 degrees Celsius, and for thawing, we did this at room temperature. We tested 1 to 5 freeze-thaw cycles to look at efficacy, and we always laid the vials on the side to make sure we did not break vials. That's always recommended when doing freeze-thaw. It allows the expansion and contraction of the liquid without breaking the glass. For microwave, we used a microwave we had in the laboratory for other microbiological purposes, and we were testing 0.5 to 5 minutes at 10% power. And at the 5 minutes, we were looking at boiling occurring, especially at the end of this, so using a heat process really in the microwave. And we had to measure sample volume after using microwave due to loss that we did experience. So one thing to note about microwave. We also looked at probe sonication. So when we're talking about sonication, there's water bath sonication and there's probe sonication. And water bath sonication from the literature can introduce inconsistencies depending on where samples are placed in the water bath or how many are placed. So with probe sonication, you get much more consistent results, so that's what we went with here. We were using a probe outfitted with a microtip that was meant to process 10 ml samples. We kept our samples in an ice bath, very important when doing probe sonication to prevent overheating of first the sample, but also of the probe sonicator. And we tested a half minute up to 10 minutes of pulse sonication, and this is where it was 5 seconds on, 1 second off of sonication. And that was in order to prevent overheating of the sample as well. For chemical lysis, we looked at Abraxas Quick Lyse, and so it comes with proprietary reagents that are added sequentially. The whole process takes about 20 minutes. And in this case, we wanted to look at less volume than they recommend and more volume than they recommend to see where their recommendations shake out when we're looking at the lysis of cells. And we also used their kit enclosed filters, which are put in the end of pipette tips, and then you end up squeezing solution through it. We also compared that with syringe filters that were glass microfiber filters that are commonly used for looking at cyanotoxins. And we finally wanted to look at something available in the lab that's been used in a few cases, just using copper sulfate. So we applied 10 to 500 milligrams per liter copper to our solutions. We allowed 20-minute exposure because we wanted to look at something equivalent to what we were doing with Abraxas Quick Lyse, and we put the samples on a shake table while this was happening. For what we looked at, we analyzed the samples for microcystin LR, as that's what these were confirmed to produce, and we used LC-MS-MS to do that. And we also wanted to look at the integrity of the cells. From previous work that was done in 4406, that aforementioned project, optical density at 730 nanometers was found to correlate with cell counts obtained with the digital flow cytometer, a flow cam that was able to image cells. And so from that, we wanted to use optical density just as a bulk measure to look at the integrity of cells after we were lysing them. So we were looking at toxin and we were looking at cells. When we look at sonication, the plot I'm showing here on the y-axis, I'm showing the normalized concentration of microcystin LR. So initially starting around 0, we haven't released the toxin yet. And then as we apply sonication, and sonication time is shown across the x-axis, we see the microcystin concentration increase as we are releasing the toxin. So we want to see that curve where it's coming up to around 1 and we're getting that complete release of cyanotoxin. And so I'm also showing the low cell density, the medium cell density, the high cell density, and the microcystin LR spike. So what we saw here is that in no case did we lose our control microcystin LR, so the sonication did not degrade the microcystin. And you can also see that around 2 to 5 minutes, that's where we are getting that complete release of toxin. So 2 up to 10 minutes was successful at releasing all the toxin. And when we look at cells, you're looking at this the reverse way. So we're starting out with a normalized concentration of cells around 1. All the cells are intact, happy, and then as we sonicate them, we are slowly killing them. So as we increase that sonication time, we want to see them going away. And that is what we see here. So also at 2 to 10 minutes, we see the degradation of cells occurring with that release of toxin. When we look at freeze-thaw, we also saw success with 1 up to 5 freeze-thaw cycles. And so essentially, looking at the x-axis here, you can see the number of freeze-thaw cycles, and at all those cycles, we kept our control microcystin, and we released all the toxin from the cells. And similarly, we saw death of the cells at each of these freeze-thaw cycles as well. And it's worth mentioning here, because I know EPA method 546 recommends 3 freeze-thaw cycles. This result should be validated with field samples that look at different morphologies of cells, but it is very promising to see that release early on in the freeze-thaw process, something to keep in mind as research continues, and we want to shorten this process as much as possible to have rapid sample analysis. When we're looking at microwave, 3 to 5 minutes proved effective here with microwave time shown on the x-axis. But it is worth noting we lost sample volume, and that limited some of our sensitivity with the measurements because having to account for sample volume loss in tandem with measuring concentration becomes a complicated process. And so I think that explains some of the noise here. And we also did not specifically see degradation of cells when we were looking at optical density. So we did not see much of a change. And so though we saw the release of toxins, we did not see the same necessary cell degradation that is always good to see just to confirm what we think is happening. So it looks like there could have been a different mechanism, or there could be aggregation or other factors at play in microwave. So while it is lysing the cells, it looks to be acting in a different way than the freeze-thaw and the sonication we've talked about so far. For Abraxas quick lyse, we looked at different ratios of the reagents. And so what I really want to point out on this slide is boxed in red is the manufacturer recommended volumes used for release. And once again, on the y-axis, we have the normalized concentration of microcystin. And we saw that the recommended reagent volumes did work. We didn't see degradation of our control microcystin. So using it as recommended did work. But it is worth mentioning here that when we were using these quick lyse reagents, we did see the occurrence of precipitates, and while these were removed well with glass microfiber syringe filters, when we were using the kit enclosed filters, we did see breakthrough of this occurring where that solution did stay a bit white and cloudy after we had filtered the samples, which could present an issue, especially if we're thinking about ELISA, looking at the optical property of the solution. And something to note, we ended up trusting the syringe filters more just based on seeing and being able to measure precipitates in the solution generated from using quick lyse. With copper sulfate, this was interesting. We did not see any release of microcystin LR within 20 minutes, going all the way up to 500 milligrams per liter. So whether it's effective or not, within 20 minutes, I can say we did not see any significant release occurring. And when we wanted to look at cells, using optical density didn't work. At this point, with these copper concentrations, we were looking at blue water, and it was affecting the optical density of the solution. So also not the greatest for looking at cell damage that has occurred. So not as effective as the other methods. Our conclusions from this first part of the study were that sonication, freeze-thaw, and Abraxas QuickLyse were all simple to use and effective. And the results we pulled from this were that we wanted to move forward using 1 freeze-thaw cycle and 5-minute sonication for the remainder of the project. This allowed us to rapidly lyse the cells. And we've summarized the results of this in a summary table that will also be part of the guidance document for this project. And with that, I would like to turn it over to Arash to discuss some of the pre-oxidation work.
So thank you, Katie. So here we are going to talk about, I pressed next slide. So here we are going to talk about pre-oxidation of the cyanobacteria cells. For these assays, we use oxidant agents that are used during drinking water treatment processes, either at pre-oxidation or post-oxidation, so ozone, chlorine, chloramine, chlorine dioxide, and permanganate. And we also use oxidant agents that are used for reservoir control, so copper sulfide and hydrogen peroxide. Our contact time was 20 minutes, and we use a range of oxidant DOC ratios. We use 5 to 6 oxidant to DOC ratios. And for the oxidant that used for reservoir treatment, so copper sulfide and hydrogen peroxide, our contact time was 24 hours. And then for the stagnation assays, so after the oxidation was done and we used quencher, we went up to 168 hours. So these are the oxidant agents and oxidation conditions used. Then, about the type of species and cells we used. We used a lab culture species of Microcystis aeruginosa, which was extracted from a bloom from Colorado River. And the cell numbers that were used during the assays were about 1 million cells per ml. We also have access to a US bloom from Great Lakes St. Mary's. It was dominant by Plantotrix, and it was about 2.7 million cells per ml at the time of the bloom when the sampling was done. We also took samples from a bloom at the Canadian side of Lake Champlain. So Lake Champlain is shared between the states of New York, Vermont, and Quebec. So we took samples from the Canadian side. And this is very specific to Lake Champlain. It was a mix of species including Anabana, Aphanatus, and Microcystis. So these were the species that we used for our oxidation assays. One thing to keep in mind that the cells that they were cultured were actually not very strong compared to the bloom cells. So you keep this in mind, these two strong and weaker arm drawings in mind, please, because you will see the impact on that during oxidation. So to measure the microcystins, we were looking at 8 different microcystin congeners. And what was interesting is that after screening for these congeners, we come to the conclusion that for the lab culture, Microcystis aeruginosa, we'll look at microcystin LR because it's producing only microcystin LR. For the US bloom, for the bloom that came from the lake, St. Mary's, it was microcystin YR, that was the toxin that we found. And for the Canadian bloom, so the bloom that was coming from the Canadian side of Lake Champlain, we detected microcystin LR. So we are focusing on these microcystin YR and LR for our different cells, and that was because that is where the toxin produced by these cells. So how did the oxidation work? For each of the ratios that we decided to do, as I said, the contact time was 20 minutes. As you can see on these graphs, we applied the oxidant dose. We did the residual curve, so we will have the decay curve for the oxidant we have, and we took the sample at 20 minutes. In some cases, we wouldn't have a residual at 20 minutes. In some cases, we would have a residual. In either way, we applied the safe quenching throughout the whole sample to make sure all the samples are comparable. So this was as you can see in this graph, we did the decay curve, or we took the sample to measure the toxins at 20 minutes for each of our oxidant DOC ratios. So Here we are going to go through each of our oxidants and the results. So we're going to start by ozone. So the graphs will show the same way for all of them. We will have the lab cultured one, we will have the Canadian bloom, and we'll have the US bloom. For all of them, on the x-axis, we have the oxidant-DOC ratio, and on the y-axis, we have the concentration of the toxins that was measured on microgram per liter. So what is important here, on each of these graphs, we have the curve, the dashed curve, that is for total toxin. And then we have the full line, which is for extracellular. And what I want you to pay attention to is the difference between these two lines, that gap. Because the total, the dashed line, presents the toxins that are within the cells and the toxins that are outside in the wire that surrounds the cells. But the full line, extracellular side, are only the toxins that are outside the cells. So as we start doing our oxidation, we're expecting to see this toxin being released from inside the cells. And then the behavior, the pattern of these two steps, the total and the extracellular, will show us when we are observing release and what is happening to these released toxins. So for example, here we can see for the lab culture, as the oxidant-DOC ratio is increasing, we are having a release of the intracellular toxins. So we're having a bit of increase in the extracellular, but the oxidation of the released toxins, so the total toxins, which are becoming more and more extracellular, is fairly fast. So at the ratio of about 0.6 or 0.5 in both cases, we are having a reduction in total concentration of our toxins. We can see that for the Canadian bloom as well. As you can see in the Canadian bloom, the curve for extracellular toxin never comes up. So that means that, but the intracellular, the total is coming down. So that means that as we're releasing the toxins, the released toxins are being oxidized very fast. And then we continue to release to the point that we get to the ratio of about 0.5, 0.6, that we are having all the toxins released and oxidized. Similar pattern was observed also for the blooms, for the US bloom samples. To the next oxidant agent that we use, chlorine, Cl2, the same, again, 20 minutes of contact. Here, again, I want you for the lab culture, Canadian bloom, and the US bloom, I want you to focus on the gap, the difference between the total cell concentration of toxins and extracellulars. And you can see, again, similar pattern was observed, but with a delay. So for all three, the lab culture, Canadian bloom, and the US bloom, we can see with the lower oxidant-DOC ratios, we actually didn't observe that much. The total concentration has stayed the same. But as we get to a higher one, particularly on 0.5, we will see that there is a complete drop in the total numbers and extracellular. So we have a release of the extracellular toxins and then their oxidation, and they become dissolved in the water. So we go to the next one. So for chloramine, we can see that actually for three of the cells, so lab cultures, Canadian bloom, and the US bloom, we had a complete vertical line for both total toxins and extracellular toxins. So we can see that for all the oxidant-DOC ratios that we used, we didn't have any release of the intracellular toxins, and the cells that the toxins were not oxidized. So we can say that the chloramine didn't have an impact on oxidation of our toxins, both intracellular and extracellular. So to the next oxidant agent. So for chlorine dioxide, we can see here the lab culture, Canadian bloom, and US bloom. The results here were a bit contradictory. We can see here for the lab culture, we actually saw the with higher oxidant-DOC ratios, we saw the release. So the toxins that we measured were completely extracellular. So we saw that the toxins are completely released. This can be due to the fact that, as I started by saying, that maybe the lab culture cells were a bit weaker in the sense that they were less healthier. So this is something to be discussed, to be studied more. It's a knowledge gap about what's the impact of the cell health or their age. We try to take them all at the stationary phase, but their health on the efficiency of oxidation, that's a knowledge gap to be answered. But we can see for the Canadian blue, we have a release So we can see that the total number was dropping and extracellular came up, but then they became parallel lines. So it means that the oxidant-DOC ratio, we had a release, we had oxidation of some of the released toxins, but then it was not efficient anymore. But it's interestingly for US bloom, we can see that we had at the ratio of about 0.2, we had complete release and complete oxidation. So that is another important point to take, that different species from different regions can react differently to our oxidant agents we use. So that is another knowledge gap, how we can generalize to a species or the cells that we can find from different regions that they're having blooms. To the next oxidant agent, so permanganate. So for permanganate, we can look at here the lab cultured, Canadian bloom, and the US bloom. We can see for the lab cultured, we can again look at the difference between the total toxins and the extracellular toxins. And we can see with higher oxidant-DOC ratios, we actually observed complete release of the toxins. All the toxins became extracellular, but there was no reduction in the, at the point, the released toxins, they were just staying dissolved in the water. But we can see for both blooms, so Canadian bloom and the US bloom, and we can observe at the specific oxidant-DOC ratios, there was obviously a release, and then the release stopped. So it means there were cells that there were still probably toxins that were intracellular. That means the cells were not completely damaged. So the release, there is a phenomenon to study here. We have to understand what is the phenomenon that's governing once the cells are damaged. What is the phenomenon governing the release of these toxins that are inside the cells? So these were the oxidant agents that are used during drinking water treatment processes. So at pre-oxidation or during the treatment, post-oxidation, for example. Then we go to our two oxidant agents that are used for the source control. So they're used at the level of the reservoir. Copper sulfate, so we can see here for the lab cultures, was fairly efficient. We had a release of the toxins, but again, we have all the toxins are released from the cells. So the cells were damaged enough to release all the toxins, but the toxins stayed as extracellular. And we can see the pattern for Canadian bloom and the US bloom were very similar, that we can see at the specific ratios, we had the cells were damaged, and we had a release of the toxins, but then the oxidant wasn't effective within that 24-hour of the contact that we had. So we can see for the US bloom, for example, we are seeing a reduction with higher oxidant-DOC ratios. We are seeing actually a reduction in the toxin concentration, but for the Canadian bloom, we can see there were still the total cells that are left within our system. And when we look at hydrogen peroxide, we again see the similar pattern. We can see for the lab culture that we actually observed that we were with our oxidant-DOC ratios very fast. We had all our toxins, they became extracellular. So hydrogen peroxide damaged the cells, and the cells released all their cells. But then the toxin stays, so the cells release all the toxins, and the toxins stayed in the water. But when you look at the Canadian bloom or the American bloom, the US bloom, we can see that the ratio between the total and extracellular toxins didn't change at all. So the cells were not damaged enough to release all their toxins, and because the total number stayed actually, in both cases of Canadian and the US bloom, they stayed very horizontal lines, so it means that there was no reduction at all in the total number of toxins that we had. This is again within that 24-hour of contact we have. So to summarize all of this, we came up with a table. This table will be also available within the guidance document. What I want you to look within this table is that 0.5 oxidant-DOC ratio. So we can see for the oxidants that are used within treatment plants, the ratio of 0.5 oxidant to DOC seems to be a ratio that is working to release the toxins and also oxidize some of our toxins. And also, this is a schematic that will be also presented within the guidance document. But what I like about this schematic is it exactly explains what I was talking about. So we have at this first, we have the healthy cells. They have toxins inside them. Then we oxidize these cells. So as we oxidize the cells, depending on the oxidant agent that we have, and depending on the state of the cells, so their health and their stage of growth, the cells will start to rupture and release some of the intracellular compounds. The phenomenon that governs that release is still an unknown. There are hypotheses involved, but we need to understand this phenomenon. Once release happens, then our oxidants will attack the toxins that are dissolved in the water. So this is very important to understand these steps, because normally people focus on oxidation of the dissolved toxins, while when you have the cell producing cells, the other things that are happening before in the presence of the cells. So at this stage, I give the talk back to Katie, which is going to talk about the effect of stagnation. Thank you.
Thanks, Arash. So yes, I will be talking about stagnation. So we're taking what Arash talked about, all with short exposure times, typically 20 minutes or less. And now we're looking at, okay, say you hit these cells with an oxidant with those short preoxidant exposures. What happens after, say, the cell has been damaged but continues to stay in your system, either retained on a filter or in sludge from settling? Will it continue to release cyanotoxins throughout that period? So we were very interested in what happened when those cells are allowed to stagnate following low oxidant exposures. So first, we're looking at plots that are similar to what Arash was showing, but we're looking at microcystin on the y-axis versus stagnation time on the x-axis. And here we're looking at the lab cultured and the US blooms for a 0.15 ozone to DOC mass ratio. What we're able to see is that there was potentially some minimal release that occurred in the first 8 to 30 hours in the US bloom, but overall we did not see much release at this ratio. And that's consistent with what we saw before, where we didn't see release. And so we can say here those cells aren't substantially damaged to the point where they're just leaking toxin throughout the whole period. They may stagnate in your system. When we're looking at chlorine and DOC of 0.15, we can see that we did see release occur in each of the blooms and the lab cultured. And so when it came to chlorine, we saw that release very quickly in the lab cultured. As we know, those are the weak cells. So we saw that release within 2 hours. In the US bloom, it was more on par with 35 hours, and in the Canadian bloom, that release within 24 hours. So we did see delayed release that you wouldn't necessarily capture just looking at the 20-minute exposure time. When it came to monochlorine, we also saw release once again. And so with the lab cultured, we saw release 12 up to 24 hours. In the US bloom, we saw release at 100 hours, so it could be quite prolonged where those cells had been damaged but just sitting. And in the Canadian bloom, we also saw release at 24 hours. So once again, that monochloramine was able to damage the cells and release the cyanotoxins. When we look at chlorine dioxide, we also saw release, and we see some of the same differences we saw when we were looking at the 20-minute exposure. So first pointing out the US bloom where the chlorine dioxide was able to release the cyanotoxin, but then also oxidize most of it. So that's why we see that total microcystin dropping in that bottom plot. When we're looking at the lab cultured on the left, we can see that release happening within 2 hours. And in the Canadian bloom, we see that release happening at 10 hours. So once again, depending on the strength of the cells, it can be slow release, it can be faster release. It definitely impacts the efficacy of the oxidant. When we look at permanganate, we do see delayed release. So this was an oxidant DOC ratio where we didn't see much release in the 20-minute exposures we were looking at, but we can see in the lab cultured here, although we did not have release at 20 minutes, we did have release of that cyanotoxin within 2 hours. And also when we look at the Canadian bloom, we see that there was some release happening within 15 hours there. Looking at copper and a 0.25 copper to DOC ratio, we do see that in the lab cultured, we had some release, whereas we truly don't see that release in the US bloom or the Canadian bloom, very similar to what we saw before, where the lab cultured cells were susceptible and experienced release up to 15 to 24 hours. Looking at a 0.4 hydrogen peroxide to DOC ratio, we also saw some release, especially in the lab cultured cells, whereas in the US bloom, we did not see release. And it was slow release, occurring up to 24 hours and later happening with those cells. So we did come up with a summary table just highlighting when we were able to see release. Admittedly, we looked at one set of oxidant to DOC ratios, and it would be interesting to probe further and expand that knowledge base. There's definitely a gap there, looking at different oxidant DOC ratios and how that can impact stagnation. What I want to highlight here is that you can see all sorts of different release results where we were seeing release at past 20 minutes all the way up to at 24 hours. So it can vary definitely by oxidant and the strength of your cells. So something that's absolutely important in water treatment. When we're looking at how this impacts how we're thinking about this issue of cyanobacteria entering the treatment plant and pre-oxidation, it truly stresses the importance of using a multi-barrier approach. So here we have a schematic. This will be included in the guidance document. But looking at partially damaged cells that, say, could be retained on a filter. If they are retained on a filter and just able to release cyanotoxins over time, it can present an issue where you would then want to look into perhaps applying a post-filter oxidant like chlorine, for example, ozone, where you know it will take care of cyanotoxins that have been released. And it may also make you consider, say, backwashing more frequently when you have a toxic cyanobacteria bloom. So it can impact how you think about those. And so while there's a knowledge gap for stagnation, we definitely see that release of cells plays an important role in looking at this overall issue. And with that, I would like to turn it over to Eric Rosenfeld to talk about utility guidance.
Thanks, Katie. So our part of this project was the enviable task of taking all of this great, incredible information that was developed by the project team and distill it down into usable and accessible guidance for the industry, both really for developing understanding and for communicating both internally and externally about this particular issue. And we took a look at many different guidance manuals. Jeanette spoke of this earlier. There's a lot of guidance out there, and we took some good things and some bad things, and we tried to minimize the use of the bad things and maximize the use of the great communication materials that are out there, both in referencing and in developing our communication methods. So generally, what is this guidance manual? Really, it's just utility guidance for managing intracellular cyanotoxins, and it's a summary of this research project. Recognizing that many utilities don't have the flexibility to use some of the suggested guidance from previous documents, such as changing sources and eliminating pre-filter oxidation. Some will be left with this need to look at this release and treat type option, which we spoke about several times throughout already today, and really to try to just develop understanding of guidelines associated with that methodology. And then again, we tried to present all this content that was developed in an accessible format, and just really try to give context and summarize existing guidance and the critical information from this project to utilities and to folks who can really use it for implementing at their facilities. And before I move any further, I wanted to acknowledge our graphics team led by Troy Oxford here at Hazen & Sawyer for this particular project. Troy did yeoman's work and an incredible job of translating information, technical information from and our ideas that were written on the back of napkins sometimes for trying to convey this information into some amazing graphical representations of some key very important concepts from this work. So I wanted to just kind of walk folks through the focus of the guidance manual, and it's really in answering questions. Answering questions about the basics. What's an intracellular versus extracellular toxin? What does this concept mean when you're talking about where these things reside and what the importance of them are within a bloom and within water treatment, within a water treatment plant. Presenting depictions of these methods for how to lyse these cells, along with critical information that describes the methods that we tested and the information that Katie developed through taking a look at how to effectively implement these mechanical and non-mechanical methods for cell lysis in order to really understand the concept of intracellular versus extracellular toxins. Again, we took a look at answering questions about the different treatment guidance that's out there. We distilled essentially down in terms of treatment strategies to 3 major treatment strategies that have been coalesced around related to guidance for treatment of cyanotoxins. And the first being most obvious, if you have the flexibility to switch sources away from the algae impacted sources. Second being sort of industry standard guidance, which was remove the cells before oxidation. And the third, recognizing the limitations on this ability to remove those cells prior to oxidizing, and really getting to the crux of this project, which is to understand and communicate the release and treat methodology. We wanted to make sure that we took a shot at explaining what switching sources meant. So there's some information here on different effective means of moving sources, everything from changing intakes in an impacted source to moving to different reservoir supplies or river supplies, or things like groundwater where it's available, or riverbank filtration. Talked a lot about summarizing impacts of removing cells or the guidance towards removing cells, and exactly why it's a good idea to do it, right? So, we know that many of the treatment processes, everything from conventional settling, if the pre-treatment is done right, the filtration will provide a nice barrier for the cyanobacteria, and items like DAF and floating these cells out. And we know these are effective means for removing the cells when available. And so we talked extensively about, or we summarized some of the work about speaking to this option. We also presented a little bit of information on some of the concerns, which are, in terms of the collecting and settling and removing of the solids that have been impacted by cells. We spoke to some of the issues that are being thought about right now in some states related to what to do with with cyanobacteria impacted solids and residuals from a water treatment plant. And then we focused significantly, and you've seen some of these pictures throughout the presentation today, because we've used them effectively to try to get across some of these messages. And again, focusing on the release and treat option, where we use oxidation of some sort to damage the cell within treatment before removal, releasing those toxins, and ensuring that there's enough of a treatment barrier after that release to effectively oxidize the released cyanotoxins. And there's a couple of things to think about that we really examined in here, and you've seen a lot of information about this today in the webinar. But we talked about the effectiveness of the oxidants used to lyse the cells, and making sure that there's enough around to take care of any released cyanotoxins. And then we got into factors to consider, which are very important to this treatment option, including bloom morphology, understanding effective extracellular and cyanotoxin treatment, and then talking about this concept that Katie just spoke about, which was the incomplete cell damage and delayed release. Considerations including, as I mentioned, bloom morphology. Depending on your morphology, it's going to be more difficult to add enough oxidant to overcome the morphological differences in order to release and then maintain enough oxidant around to effectively oxidize the remaining extracellular toxin. Again, different oxidants affect cyanotoxin oxidation at different rates. We've provided a lot of the summary information that's known to date within the manual. And then finally, as Katie showed, and we tried to summarize the concept of incomplete cell damage, delayed release, and really why this speaks to the take-home message, which is how important it is to understand your system and the capabilities of your system, to understand which treatment option is most applicable to you, and if it becomes that you need to use a release and treat method, it's really important to understand the risks associated with that method and threshold concentrations of oxidants that need to be around afterwards, either in follow-up treatment or remaining after the lysine of the cells occurs, in order to understand, make sure you have effective treatment. So we're really describing and advocating for a multi-barrier approach, as you said several times, and ensuring that that effective treatment does occur. And then finally, I'd like to wrap it up with a section that we put in there, which describes future research that really needs to be addressed related to this release and treat option. Some of the variables we've discussed previously are still unknown and need to be addressed as moving forward. Would be great to, as Eric will hopefully have a chance to talk about later, and Jeanette has already mentioned, to get some full-scale data from case studies that have effectively used this methodology. And of course, there's always innovations in terms of understanding what cells are out there and what effective oxidation we can employ to address those the contaminants related to the various cyanobacteria. So with that, I'll turn it over to Craig to speak about the final piece of the project, which is the CyanoTOX tool.
Thank you very much, Eric. Yeah, I'm going to talk about the Hayes and Adams CyanoTOX tool. Version 1 has been available online for a considerable period of time. Version 2 has been out for about a year as well, and version 3 will be coming out in the next few weeks. I'll talk about each one of these. So the purpose of CyanoTOX is to be able to predict removal of extracellular toxins under a range of conditions. And version 3 has, as you'll see here in a minute, the ability to examine impacts of intracellular toxin release within a water treatment plant. And really it's for sensitivity analysis and bracketing of outcomes for various types of water quality and treatment scenarios. It's an evolving tool over time. This is the algorithm. I'm not going to go over it now. This is all available in peer-reviewed papers as well as within the tool itself. So this is the kinetics that is used. It's all peer-reviewed kinetics. We have 3 different cyanotoxins, microcystin LR, Salindus bromopsin, and anatoxin A. For each one, we have 5 oxidants, and those are rate constants on the y-axis and pH on the the x-axis, and you see for some of the oxidants there's a strong effect of pH, which is important. The exposure, or CT, can be determined 3 ways within the program. One is by entering an oxidant dose and an instantaneous oxidant demand, decay rate, and contact time, and the program will calculate the CT. Or conservatively, you can pick off a CT by the residual concentration and contact time, such as within a contactor, or you can enter CT directly. So this is an example of one scenario, microcystin LR with free chlorine. You can see that this is a pH 8.2, a certain temperature. It's microcystin LR, initial concentration of 14 with a target concentration of the health advisory using free chlorine. And then we have a baffling factor set of 0.3, an oxidant dose, instantaneous demand, contact time. And you can see the results then on the right, presented the same results in a number of different ways. The top one is the concentration micrograms per liter, and we see it drops down to about 3.5 micrograms per liter. If instead that was everything the same conditions, same contactor, but it's slindospermopsin, you see we get much better removal, and quantitatively it's less than the 0.0. Now, and there are the results there. So if we had microcystin now with a different oxidant, permanganate, we get extremely good removal as opposed to with free chlorine, which we got a lot less. And another example under the same conditions. And then if we go to slindospermopsin with permanganate, we get very little removal. So the tool can be used to examine these different combinations of oxidant and toxin under different conditions. So it can also be looked at to examine non-idealities within our contactors, for example. This is a baffle factor of 0.3, and I've drawn a schematic sort of a contactor with poor baffling. And if you look on the right, you see that the removal it takes us down to about 3 micrograms per liter from the 14. If we put in some extra baffles into that same contactor and our baffle factor goes up to 0.5, we see we get a much better removal than just by simply putting in baffles. And if we put in even better baffling, and our baffling factor went up to about 0.7, we get near complete removal. So this shows you how you could use CyanoTOX to help with plant optimization, design, and so on. Another thing that we can look at are pH effects. So we all know that free chlorine is hypochlorous acid and hypochlorite. 2 forms, the pK is about 7.6. So above that, you're a majority hypochlorite. Below 7.6, you're a majority hypochlorous acid. Hypochlorous acid is about 100 times stronger oxidant. So here's pH 9.2. We get some removal, not great. If we go to 8.2, we get much better removal because we're shifting over to hypochlorous acid. And if you go to 7.2, you get much better removal. So again, we can use CyanoTOX for looking at water quality parameters. What about mixtures? Well, not all microcystins are oxidized at the same rate. If this were a mixture of La, Ly, and Lf, we see the removal that we get there indicated by the blue line. What if we were a mixture of Lr, Rr, and Yr, which are removed more quickly? We get a much better removal. So CyanoTOX allows you to look at that. Now, I want to talk briefly about the release module that has been developed. It's under review and testing right now, and it'll be released maybe within weeks, hopefully. So we've seen this plot. So when you hit a cell, a cyanobacteria cell with an oxidant, you get release, and then the free chlorine could oxidize other things as well. So the way this module is set up is you have a water treatment plant, and you can enter oxidants at 3 locations for this program. One is at the intake, one is in the rapid mix, and one is at the contactor. And there we go. And so then you can enter the temperature, the toxin itself, what the total toxin, intra plus extracellular, and what the extracellular toxins are, and then those are the 2 tests we tend to run, right? And then you have the intracellular toxin. Then we can also enter the oxidant information for each zone. And the example that's set up is we have permanganate coming in at the intake, we have free chlorine at the rapid mix, and we have the contactor with ozone. For each one, we have a CT, we have a pH, and then we have an assumed release rate from the cells. And this is what the speakers have been talking about today. And we could put in what we guess the release would be, but then we can also bracket it with faster and slower and see what the effect is. And then we can also include a removal by PAC, by settling of solids in the settling basins, and removal on the filter of the intracellular toxin, and also the release of intracellular toxin on the filter. And then we put in the contact times, or hydraulic retention times, I should say, for each basin. So let's look at an example. So here we have an example that we're oxidizing microcystin LR, and expand that, there we go. And so you see, after 30 minutes, that's the end of the intake, and then at 50 minutes is the end of flocculation. At 170 minutes is the end of sedimentation, and then the end of the contactor is at 230. We see in the first zone we have permanganate going in, and I'm assuming a slow release. Second zone we have monochloramine, and the third zone, the contactor, we have free chlorine. So with slow release, if you look, we have up in the front, we get a very rapid oxidation of the microcystin LR by permanganate, and then a slow release. Then we get into the rapid mix, flocculation, sedimentation. We get a continued release throughout. So you can see a decrease in the intracellular toxin and an increase in the extracellular toxin. Then after the filter, we hit free chlorine and it's oxidized. What if instead we had, oh, here are the zones. There we go. What if instead we had a moderate release due to the permanganate oxidation of the cells? Well, what we see now is, again, a rapid oxidation of the microcystin LR by permanganate. But then when we hit the flocculation sedimentation, that moderate rate of release continues to release that intracellular toxin, which then builds up as extracellular toxin. In this example, we have monochloramine in there, so we don't have much oxidation going on. So when we hit the filter, coming out of the filter, we have a fairly high concentration now of extracellular toxin, whereas with a slow release, we had a very low concentration. But what if we do another case that we got a very fast release of the microcystin in the intake due to the permanganate oxidation? In this case, we get a very fast release and subsequent oxidation within that pipe of the microcystin by the permanganate within that 30 minutes. And then again, we have a low concentration of the, sorry about that, low concentration of microcystin LR coming out of the filter. So what's interesting about this is you can examine many different scenarios with different oxidants, CTs, pH, assuming slow release, fast release, and even different conditions with PAC and settling of solids. But if you, just to remind you, with a slow release, we had low concentrations of extracellular coming out of the filter. With fast release, we had low concentrations, but with an intermediate release, we had higher concentrations. And so this program will allow you, or allow all of us, to examine different scenarios with respect to cell release of toxins within the water treatment plant. And so version 2 has been available for quite some time. Version 3, again, is being tested right now by others, and version 3 will be coming out shortly. With that, I'll turn it back to Jeanette to talk about some of the Water Research Foundation projects.
Myself on unmute, it will be much better. Thank you, everybody. That was really outstanding. I think that's going to be really a very important project, and as I say, we'll have many, many more. So I talked a little bit about the foundation project earlier, but I wanted to, and I mentioned the projects that were done previously, and the summary is in the state of the science. I talked about the 3 recent projects, the communication, the expert workshop, and the performance evaluation. And I mentioned the 3 projects that are ongoing, the refinement and standardization of cyanotoxin methods, the guidance evaluation, and the utility response. But since Dr. Eric Wirth is the project investigator, and actually most of his team here are started the project, what we call 4912, I'm going to let Eric or any of his team, Arash or whatever, thank you all, to talk us a little bit about this project that you are starting, and if you need any input from our utilities and everything else. So Eric, I think I would love you to tell us about your new project.
All right, thanks, Jeanette. Yeah, I included just 2 slides here on the new project that was awarded, I think, 2 months ago, titled Developing Guidance for Assessment and Evaluation of Harmful Algal Blooms and Implementation of Control Strategies in Source Water. And once again, we have an outstanding project team, Polytechnic Montreal, University of Adelaide, Hazen, and University of Toronto are all on board, along with several utility and technology participants from the US, Canada, Europe, and Australia. And what are we going to do? I've highlighted our research approach here in this slide. We're going to start off with a critical review of early warning systems and source water control strategies, so things like algicide, sonication, and other methods. The next task will be summarizing utility practices. So if anyone on the webcast would like to participate in the survey, or if you have a good case study or SOP that you believe the project could benefit from, please let us know. You can drop a comment in the Q&A part at the bottom of the screen, and that way we can follow up. Another part is some innovation evaluations. We're going to look at ATP-based approaches to assess early warning as well as source water control strategies, and that's what's shown in the slide right there. We recently published some work too regarding the use of ATP to assess treatment efficacy, as it ties into all the work that you just saw on the webcast. So we may be able to assess cell damage and develop slightly better framework regarding intracellular release if we can base that off of metrics like ATP. So look for that. Also, we are going to perform a survey of benthic cyanobacteria. So we're also seeking plants that suspect they have issues with benthic cyanobacteria and the production of toxins or taste and odor compounds from benthics. So far, a lot of the focus has been on planktonic cyanobacteria or free-floating cyanobacteria, so we want to take a look at the attached stuff. And lastly will be the development of a guidance document and decision trees. And hopefully we'll be able to create some great graphical illustrations of different concepts related to early warning and source control, similar to the ones that you saw that were produced by the Hazen team, Eric and Troy. So now I'll turn it back to Jeanette, I guess, to facilitate the Q&A portion of the webcast.
If I could start. So before, I mentioned another project, and I don't have a slide for that because the principal investigator is not here, but we have a co-principal investigator. And the project that is about to start, actually, the number is 4914. And the title is Utility Response to Cyanobacteria Cyanotoxin Events, Case Studies and Lessons Learned. So the project is going to gather case studies for utilities that have experienced cyanobacterial events and their experiences in responding to the event. The project, the outcome will be a guidance for a proactive prevention, that's measures on avoiding cyanotoxin problems, and to develop guidelines for utilities to develop into the program to to manage the cyanotoxin. So we'll hear more, and some of the information will be on our website. We'll have the scope of work, and we'll have, so if you have any question, please contact us, and then we'll see how to get involved in this project. Now, 2 questions. As you may have guessed, we're going to have more questions than we have time to respond to. So I'm just going to pick up some of the questions, and we promise you that all the questions will be answered. The one we are going to address now will be fine. The whole audience can hear them, and we'll provide all the answers to the questions that we haven't had time to address. So as I mentioned, our speakers, their work is not done today. So after the webcast, they will have to answer your questions. So I'm going to go a very general question, one that I can answer myself. That's the only one. So somebody asked is for the guidance manual that Eric and the Erics have presented. Is it available publication? No, we are in the publication process. The project is finished, and we estimate the publication date to be in a month or so. So we will have a press release when it's available for you to access. So, and again, let us know when if you have questions. So I'm going to, I'm going to pick up just some questions as I want to, and that's a very interesting one, and it's going to be to Craig and anybody who can say. It's a very general questions. So how can small public water system use CyanoTOX?
Sure, thanks you, Jeanette. Briefly, I would say that this tool would allow at a small or large water utility the ability for a manager to examine different scenarios in advance. It's a learning tool. It's also a tool that one could be using real time. So I don't think the size of the plant really affects, its utility.
Thank you, Craig. Anybody want to add to this question, or I think Craig addressed it? The other question, I'm sorry, go ahead.
Jeanette, I just wanted to add that it's available on the AWWA website. Craig mentioned that a couple times, but maybe we can send that website out, Craig.
Right, it's freely downloadable. It's freely downloadable, and it's Excel-based. Sorry, Jeanette, go ahead.
No, I'm saying is that the question was specifically to the guidance for the intracellular, the one that was presented. Adam, you are absolutely right. It is basically the guidance for utility manager is available on our website. This one is for this project for 692. They're asking about the intracellular release. So anyway, so the resources between the AWW and us, you can find a lot of information for the CyanoTOX Tool. So, and the question is going to go to Eric Wirt, a very simple question. How did you select the oxidant to be tested for the, both for the project, for the 4406 and for the 692? How did you select this oxidant?
Yeah, thanks, Jeanette. So, regarding the 4406 project, that was really our first shot at doing experiments like this. And we picked ozone, chlorine, chloramine, chlorine dioxide as being pretty commonly used oxidants in drinking water treatment plants. And along with knowing that, ozone and free chlorine tend to be stronger, and chlorine dioxide, whereas chloramine may be a weaker oxidant, we felt we had a pretty good range to work with. And after presenting at conferences, we had a lot of feedback regarding expanding the types of oxidants that we looked at, and we also had a lot of feedback regarding using algicides. So that's how we picked those up as part of the 4692 project, where we picked up permanganate as well as peroxide and copper. So we tried to broaden it that way, and hopefully we've covered a lot of ground now with respect to the use of oxidants.
Thank you, Eric. There's so many questions to choose from, so I think this question will probably go to Arash. During the chlorine dioxide experiment, did you measure chloride in the finished water, treated water? Did you measure the chloride?
We tried, but we were not able to measure all the time. Let's say that's one of the challenges we're facing.
Yeah. So I think this question go to anybody. I mean, Katie, Craig, or whatever. What is the minimum detection limit for MCYR, not LR? Do we have that on the top of your head?
I can speak to, at Southern Nevada Water Authority, our method reporting limit at least was 0.5 micrograms per liter for YR, as well as LR. Actually, the actual limit of quantitation would probably be lower, but for the 8 congeners we tested, our reporting limit was 0.5 micrograms per liter.
Thank you, Katie. Okay, I have another question for you, Katie. How were the low, medium, and high cyanobacteria cell concentration cultures? What am I missing? Half of the screen here. Prepared. How are they prepared?
So for those experiments, we prepared by culturing them in batches and flasks in an incubator. But then all the cells, we ended up taking those suspensions, the cultures, and spinning them down in a centrifuge, rinsing them with 10 millimolar phosphate buffer, pH 7.5, rinsing and centrifuging a process of 3 times to get those cells nice and clean. And then after that, suspending them in a bit of 1 millimolar phosphate buffer. And we spiked those into more phosphate buffer to the concentration we were looking for. We confirmed we were getting the concentrations we were seeking with flow cams, so we were able to get cell counts to confirm that we got what we wanted from spiking in that cell concentration that we prepared from cultures.
Okay, thank you, Katie. Again, a general question, and I think I'm just going to let Eric work because that's obvious. We did not mention activated carbon, PAC, or GAC in the project, so I think.
Yeah, that's a great comment. And as far as this project goes, we were looking at oxidative release of intracellular toxin, and that is the release part, getting it out of the cell. And as we tried to emphasize today, you also need the treat part, either simultaneously with the use of that same oxidant or through a downstream process. And I think activated carbon, PAC, or GAC, would fit that treatment component. So if you use an upstream oxidant, get the toxin out of the cell, only activated carbon would be a tool in the toolbox for the treatment part.
And I should add that version 3 allows both of those, powdered activated carbon or removal by GAC on the filter as a filter cap.
Mm-hmm. Thank you. And we have a lot of projects on activated carbon, so please visit our website. This is again a general question. Any one of you can answer. It's regarding. I think Eric, you did some of the 4406. It is any consideration of formation of THMs and HAAs from cyanobacteria?
Yeah, another good question that we get a lot is, I guess, the first part of that is, are you releasing intracellular dissolved organic carbon? And throughout most of our studies, the amount of DOC release has been marginal. And by marginal, I'll say about a 0.5 milligram per liter or less. I know that there are reports that exceed that, but that's kind of been our experience. So what we did to try to evaluate the DBP question is take a bunch of cells, grow them up, and then extract. We did freeze thaw a few times, so we had this extract of the intracellular dissolved organic carbon. And then we chlorinated that. And we did find that it formed both chlorinated byproducts as well as nitrogenous byproducts under FP formation conditions, which is very high either free chlorine or chloramine doses. At drinking water doses, we still saw some production of the chlorinated or the carbonaceous ones, not so much of the nitrogenous ones, because there's also dissolved organic nitrogen that can be present. It wasn't a strong focus as part of this work and this project, the 4692. So if you're going to go into the Foundation website hoping to find that information, it's all written up in part of 4406.
Thank you, Eric. I am going to ask, maybe it will be our last question answered aloud, out loud. So this is for Arash. We're talking about Canadian versus U.S. So the question is, can we say Canadian bloom versus U.S.? Simple point may show differences between microcystis dominant and philanthropic filamentous bacteria. So it's a general question. It's more phycology, but if you have any insight, Arash or anybody. So what's the difference between Canadian versus U.S.?
So yes, in this case, for these two, that's for the lake that came from the U.S. and the Canadian side of Lake Champlain, we can say that yes, in that one lake that we had the bloom from the U.S., we had one species that was present, and while the Canadian side of Lake Champlain, that's actually we've observed that in many years that is specific to this lake, that there are several species that are present at fairly high numbers. So what we can see between these two blooms is actually we're studying the bloom that had one species as a dominant species and the bloom that has several species that are present. So we can actually put it this way, a bloom with one dominant species versus a bloom with several present dominant species. Let's put it this way. And then also you can have different species. So here we don't want, yes, because the morphology of these species are different, we didn't get that to that. That is actually, it needs by itself a full-on project.
Thank you, Arash. I think we're out of time. I cannot wait. Eric, you better finish this, Rick Rosenfeld, this guidance, because it sounds like a very nice tool, and I would like to see that soon, to play with it. I think we are out of time, so I'm going to thank you for being patient and listening to all this great information. Again, please don't forget to fill the survey. It's going to be very important for us. Anything you can put in the survey, we would really use that to improve our webcast. If you have any questions, you have my email address here, Jeanette DTR@WRF.org. And I will encourage you really to visit our website, because we could not present in an hour and a half everything we have done, and hope to see you in future webcasts. We're going to have and one thing is that I would like to, if any people from the Pacific Northwest are attending, we're having a utility workshop on May 29th in Tacoma. So we'll hear about that, and please attend. Some of this work will be presented and much, much more. And with that, I'm going to set you free to do your work. Thanks so much, and be in touch. Bye-bye.